The concept of solubility is incredibly important for what we're about to do next. To really truly understand some chemical reactions, we do need to understand how these chemicals will behave in an aqueous solution when they're dissolved in water. So it's really important to make sure that you have a copy of the solubility rules out and in front of you as we go into this next section. I'd like to discuss with you something called a particulate diagram. This is just a simple way of imagining what is actually happening on the inside of a beaker. Now, these chemicals are so incredibly tiny that we really can't see what it is that we're doing. But it's important to be able to kind of think about it. So let's start off with a little bit of an example. Let's think about what CaCl2 would look like if we would dissolve it inside of a beaker. So let's get a beaker. And for the purpose of this particulate diagram, let's draw the different ions here as little circles. So I'm going to draw a red circle for my cation. In this case, it's going to be Ca2 plus ion. And a little blue circle for my negative anion. In this case, it's going to be the chloride Cl1 minus ion. Well, before I would throw any of the CaCl2 into the water, it would start its life out as being a solid. On dry land, it's a solid. But when we throw it into the beaker, it has the opportunity to dissociate. Now, soluble compounds, those that we would be marking as being AQ, should end up breaking apart when they go into that water. So this would be a particulate diagram for CaCl2 aqueous, calcium chloride aqueous compound. When we put it into water, each ion breaks apart. Now notice that according to the formula, we should have one calcium, that's the red sphere, and two chlorines, those are the blue spheres. Let's take a look and see what this might look like with another compound. Here is MgOH2. Now in this case, let's pretend that red still represents my cation and blue still represents my anion. Now before we would put this into the beaker, of course, MgOH2 would start its life off as being a solid. Now, according to the solubility rules, we predict that MgOH2 should have a solid state symbol. So when we throw him into the water, it really doesn't matter what we do. He sticks together. He does not dissociate. That is what the solid state symbol truly means and what this will actually look like. So the most important thing that you can understand today would be simply this. The solid state symbol means that these ionic compounds stick together when they're in water. AQ means that the ions break apart. Let's take a look at another example. What about Na3PO4 ion? Now in this case, notice I've added 3 red spheres to indicate that I have 3 Na1 plus ions and 1 blue sphere to indicate my 1 PO4 3 minus ion. Our solubility rules do state that this is expected to be AQ, aqueous. So when I throw him into water, this compound should dissociate. Now, where particulate diagrams really come in handy is when we start to take a look at chemical reactions. So in this case, we're starting to build a chemical reaction. In this case, it's going to be between sodium iodide aqueous and silver nitrate aqueous. Let's draw the particulate representations for these two chemicals. So before any chemical reaction actually occurs, we can see the Na and the I separated inside of the beaker, and the Ag and the NO3 separated from each other inside of a beaker. Now, if this is going to be a true chemical reaction, we are going to have to put them together. So we need a product side beaker. And eventually, we're going to imagine that we're pouring the contents from these original reactant beakers together on the product side. Now, what I want you to envision is that once we do, in fact, pour all of those particles together, that they're going to be mixing around with each other over and over and over again. They're mixing around, and then all of a sudden, it's possible that 2 of these ions are going to bounce into one another. Now we would need our solubility rules in front of us to find out, is this a case where they just simply bounce off of each other and remain AQ? Or do we predict that that combination creates a solid? Because remember, solids stick together. And in this case, you'll notice that a blue sphere and a yellow sphere have come in contact with one another. That means an Ag and an I are now touching. Well, according to our solubility rules, when Ag meets I, that's creating a solid, and solids stick together. So after this collision, those two ions no longer have the ability to separate. They stick together and a precipitate has formed. So after the chemical reaction, we'll actually see that the blue and yellow combination, they sink down to the bottom of the beaker, and we can actually see that the little green and red left over can still freely rotate around each other inside the remainder of our beaker. Now, what we can do then is to try and represent the products that have actually formed. We know that when Ag and I hit each other inside of the beaker, that they formed an insoluble combination. That's solid state symbol. But what's left over inside of the beaker, that's the Na and the NO3 ion. We can put them next to each other as long as we give them the AQ state symbol. That means that when they're in water, they're actually separated. Let's take a look at another example. Let's take a look at the combination of NaI and PbNO3 Now, I tried to put the little circles up on top of those chemicals so that you could see which is which. So Na this time is going to be red, I is going to be blue, Pb is going to be yellow, and NO3 is going to be green. Now, notice in this example, I put in 2 green dots to represent the 2 NO3 ions that you have for each one Pb. Now, that ratio is really, really important. Notice also in the first beaker, I have 2 reds and 2 blues. It really doesn't matter how many of these particles that I decide to put in, as long as that ratio is correct. There should be 1 blue for every 1 red. Now, let's envision what could potentially happen once I pour these things together. Again, one of the very first steps is that they are going to start mixing around and mixing around. And then suddenly I may find that a collision is no longer able to separate. In this case, it looks like the Pb has met the I. Now, Pb in this example would have a positive 2 charge. Iodine in this case has a -1 charge. That's why it actually takes 2 blue iodines for every 1 yellow Pb2+. That creates a neutral overall charge. But again, according to solubility rules, when Pb meets I on the inside of the container, that creates a collision that cannot separate. That gets a solid state symbol, and solids stick together. We have just formed yet another precipitate. So just in like manner, what happened before, our solid is going to sink down to the bottom of the beaker, and our little other ions, which are still bumping into each other but do not create that solid, are free to rotate in the rest of the beaker. Now, we could actually, again, represent what that looks like on the product side. So we can say that the Pb and the I have come together and they formed a solid precipitate, whereas the Na and the NO3 remain dissolved, dissociated, separated from each other, and in the solution. Now, for this video, it's not so important that you're able to write the correct chemical formulas for these products. I simply want you to think about how we would be able to predict these products. We need to think about these ions all together at the same time, bumping into each other. And is there a combination that will produce a solid?